afternoon, everyone. My name is Chen, and it's my great honor to be here to introduce our work on constant overall OFDM with selective mapping. And our research focused on providing a novel low PAPR waveform to improve power amplifier efficiency, which is beneficial for enabling low power wireless sensor network. And this presentation will cover the following 5 parts: background and problem, system model of COFDM, and our proposed selective mapping method, inspiration result, and conclusion. Now, let me start by discussing the background and the challenges we are addressing. As we move towards this generation and beyond, communication systems face increasingly strict requirements, especially in terms of energy efficiency. It's this project that future communication will need 10 to 100 times higher energy efficiency compared to current standard. And another key challenge is the massive device connectivity, where networks are expected to support up to 10 million devices per square kilometer. To satisfy this requirement, wireless sensor network WSN require low power consumption for practical application. Power amplifier, which are some of the biggest energy users in WSN, play an important role in achieving ultra-low power communication. One of the problems is that due to the non-ideal linearity of practical power amplifier, a high PAPR will force the amplifier to operate in a power back-off mode to avoid distortion, leading to significant energy loss. Traditional OFDM is widely used in communication systems due to its robustness. However, OFDM has extremely high PAPR, as we mentioned before, which will reduce power amplifier efficiency and result in higher power consumption. To address this challenge, we turn to constant envelope OFDM, which apply phase modulation to generate a constant envelope signal. This allows power amplifier to operate at their most efficient point without the need for power backup, addressing the PAPR problem directly. Hence, combined with this advantage, COFDM is considered as a potential technique scheme in the future communication systems. Moving on to the system model, the COFDM structure is built on phase modulation. While COFDM reduces PAPR, the use of phase modulation introduces a new challenge: phase wrapping. Phase wrapping occurs when the phase of a signal exceeds the range of minor pi to pi due to the noise or signal distortion, leading to BER performance loss. So the question is, the challenge is how to minimize phase wrapping while preserving the constant envelope property of COFDM. To address the phase wrapping issue, we propose combining the selective mapping technique with the COFDM system. As shown in this figure, the input bits are first modulated into constellation symbol. Multiple candidate sequences are then generated, and the one with the fewest phase drop is selected for transmission, followed by phase modulation. By doing so, we can effectively reduce the negative effect of phase wrapping. Now let me explain the selective mapping technique in more detail. First, the original transmitted constellation symbols are generated according to the important bits. Then T different phase sequences are generated to form potential candidates. Upon this, the original transmitted sequence is multiplied element by element with different phase sequences. Following by this, we apply the compressed conjugate operation And then we can obtain the moderated OFDM symbol in the frequency domain. And finally, we can obtain the transmitted sequences with minimized number of phase drop from the P sequences. The important part of this sequencing is determining the phase drop criteria. A phase drop occurs when the phase should exceed a certain threshold, typically around pi, which causes phase swapping. And following this, we can define the number of phase drop in our sequences as following. And the wheel can be used to determine which sequences to be selected. To obtain the optimized threshold, we rely on the 3-sigma rule, where nearly all phase noise will vary fall within 3 standard deviations. By confirming the variance of phase noise, we can set a proper threshold to account for the number of phase drops that the OFDM signal may experience. Let us move on to the simulation result. In Figure 1, we show how the number of candidate sequences affect the BER performance of COFDM SLN system. As the number of candidates increase, the BER improves significantly. Interestingly, the BER performance of P equal to A closely approaches the optimized performance observed for P equal to 10, making it a suitable choice for balancing performance and capacity. Hence, in the following simulation, we set P equal to 8. And in the Figure 2, we compare the BER performance of the proposed COFDM SL system with the conventional COFDM system under different moderation ingress variables. The results clearly show that the proposed system significantly enhanced BER performance, particularly at higher moderation indexes. And this improvement across different situations through the effectiveness of the SLN technique in addressing phase swapping issue. And it is worth knowing that the performance improvement is achieved with only a slight increase in capacity, making it an attractive solution for future energy efficiency wireless communication systems. And in conclusion, we have proposed a novel method that integrates the selective mapping technique into the COFDM system to address the phase swapping problem. By selecting a simulation result shows that the proposed COFDM SLN system significantly enhanced BER performance compared to conventional COFDM, particularly at higher moderation indexes, with only a slight increase in capacity. This making it a strong candidate for energy efficiency wireless communication system. And that's all. Thank you. Thank you for listening.